Hey guys, in this video I will present a solution to Romanian Masters of Mathematics 2023 problem 6. We are given three non-negative integers r, g and b, and the graph g equals v, e that is undirected and that has r plus g plus b plus 1 vertices. We color its edges red, green and blue. Now it is known that g contains three spanning trees, tr, tg and tb, such that tr contains exactly r red edges, tg exactly g green edges, and tb exactly b blue edges. And now we shall prove that there exists one spanning tree of g which contains at the same time exactly r red, g green and b blue edges. At first we want to confirm that it is generally possible that such a tree exists. And to do that we know that it is known that a tree with v vertices has exactly e minus 1 edges, and such spanning tree would also have r plus g plus b plus 1 vertices and therefore r plus g plus b edges, and therefore if the coloring works out, it is indeed possible that we can find such a tree. The general idea for this solution is that we can change a spanning tree very slightly such that we obtain a new one. And it makes sense that we want to take a look at such an operation in this problem, because what we want in the end is to get a tree that has all of the properties for tr and tg and tb. And so we might want to start with one such tree or something like that, and then do slight changes to it such that we obtain the desired one. Because the number of edges for a spanning tree of a constant number of vertices is also constant, the easiest such operation is removing an edge and adding a new one. So let us define the set of such edges. We call it det for a given edge e in a spanning tree t, and then we define det as the set of edges f in e such that t minus e plus f is a spanning tree of g. Here I want to note that this notation refers to removing e from the edge set of t and then adding f. Let me draw in a quick picture so we can understand det better. We notice that det consists of all the edges between the two connected components of t minus e. This is not hard to prove, but for the sake of completeness you can look it up in the PDF on our website as always. Before we start, we also want to give the red, green and blue edges some names for a little more concise notation. So let us define er to be the set of e in e such that e is red, and define eg and eb analogously. As I already said, we want to use tr, tg and tb and that operation to get our desired tree. Even better than tr, tg and tb, we can define t as a spanning tree of g such that it has exactly r red edges. And here I want to note that this notation refers to the edge set of t, so this is the set of all red edges in t. And we know that such a tree exists by the definition of tr, and out of those trees we want to choose one such that its number of green edges differs to the desired amount of g by some minimal value. The problem now becomes to prove that this quantity is indeed equal to 0. So, for the sake of contradiction, let us assume that it is not 0, or in other words, the number of green edges in t is not equal to g. Because t has exactly r plus g plus b edges, as discussed before, this quantity must exactly be equal if we replace all the g's by b's, and therefore this situation is symmetric, and so we can moreover, without loss of generality, assume that this quantity is indeed less than G, and therefore we must also have that T has more than B blue edges. From this definition, we can immediately deduce that for any blue edge E in the tree T, the set DET does not contain any green edges, or else we could do that operation to obtain another tree with R red edges where this quantity is smaller. So let me write this down. We have for any blue edge E in E of T that the set of green edges in DET is empty. On the other hand, let me note that T contains more blue edges than TB. So it feels like we must be able to find some blue edge E and E of T such that DET does not only consist of blue edges, because otherwise it would feel like any spanning subgraph of G must have at least as many blue edges as T, which contradicts the existence of TB. So let us try to prove that there exists a blue edge E0 in E of T, such that there exists a non-blue edge in DE0T. The sketch goes as follows. We know that because T has more blue edges than TB, the graph T minus EB, which consists of all the non-blue edges in T, has more components than connected components than TB minus EB. Therefore, we find an edge F0 in that forest that connects two different connected components in T minus EB. Firstly, I want to note that this fact implies that F0 is not a blue edge, and furthermore, because T is a spanning tree of G, we note that T plus F0 must contain some cycle K, because F0 is of course not an element of T. To finish, I want to note that because F0 connects two different components of T minus EB, the graph T minus EB plus F0 is cycle free. Therefore, T minus EB plus F0 does not contain K, which is a subgraph of T plus F0, and hence K contains a blue edge, which we want to call E0. So, as desired, we found a blue edge E0 in T, such that T plus F0 contains exactly one cycle as always, but that cycle contains E0, and therefore T minus E0 plus F0 is again a tree. And because F0 is not blue, this is exactly what we wanted. Now, we also know due to this that F0 cannot be green. And therefore, I'm going to write down that we find a blue edge E0 and a red edge F0 in DE0T. Of course, we now want to consider the graph that we obtain from T by removing E0 and adding F0. Let's call it T hat. And because T had exactly R red edges, T hat must now have R plus 1 red edges and has one blue edge less than T. This allows us to proceed very similarly as we did before. Because if we find any red edge E in T hat and any green edge within DE T hat, then we can do the operation T hat minus E plus that edge to obtain a new spanning tree of G with exactly R red edges again and one less blue edge than T, which contradicts the definition of T. So let me write down that for any red edge in T hat, we have that DE T hat does not contain any green edge. I have drawn in a picture where all the edges that are in T or T hat are solid lines. And I want to note that we see here that T and T hat are really similar trees. In particular, the two forests t minus e0 and t hat minus f0 are indeed equal. That is why the combination of these two facts is really useful for us. So t and t hat are really similar, and for t, any blue edge satisfies that det does not contain green edges, and for t hat the same goes for that for any red edge e, det hat does not contain any green edge. Because t and t hat contain less than g edges, that should be enough to prove, or is enough to prove, that we cannot find g edges that do not contain a cycle, which is a contradiction because the set of edges of tg intersected with eg is exactly such a set of edges. In other words, we want to prove that a graph consisting only of green edges has very many or too many components. When taking a look at components of a graph, a useful operation is the contraction operation. In particular, we want to take a look at the graph T contracted by EG. And this is the graph consisting of all of the connected components of green edges contracted. So you can think of these four vertices now as one, so squeeze them together to one vertex, and all of the outgoing edges remain, and of course these vertices are maintained, and we can also think of these two vertices in that graph as one. Hence, the vertices of T contracted by EG correspond to connected components of the graph consisting of the edges in EG, or in other words, the number of vertices in T contracted by EG. And again, this notation refers to the set of vertices of that graph. So this number of vertices is equal to the number of components in the graph only consisting of the edges EG. Let us call this quantity from now on k. Recall that we wish to prove that k is larger than the number of connected components of a forest with exactly g edges, because that is a contradiction, since we can find such a forest, namely the set of green edges in Tg, that is a subgraph of this one. So let me write down that we want to prove k greater than r plus b plus 1, the number of components of a forest with g edges. We know the number of edges in T/EG because this graph contains exactly the edges of T that are not green. And now we want to get a lower bound on its number of vertices. And to do that, we take a look at this picture, and we see that this behavior of the green edges that is restricted by these two facts that we found out earlier kind of implies that all of these green components only lie in green components of T as well. So what I mean by that is that we cannot have a green edge that goes between some edges where some of them are red or blue, but all of these green components of edges in G must also lie in green components of edges in T. And this kind of tells us that if we contract them, we again get a tree. And in particular, we want to prove that this graph, T/EG, does not contain a cycle. Because what we know is that a cycle-free graph can have at least one less edge than its number of vertices, and so we can bound its number of vertices from below. Let us assume that there exists a cycle in T/EG, or in other words, that we can find a cycle in T plus EG that does not only consist of green edges. So let me write that down. We assume that there is a cycle C in T plus EG, and in that cycle we find an edge E that is not green. If we call its endpoints V and W, then this tells us that there exists a VW path P, namely C minus E, in the graph T plus EG minus e. By this characterization of det, and because the endpoints of p lie in different connected components of t minus e, we know that there exists some edge f in e of p that also lies in det. Furthermore, p lies in t plus eg minus e, so this is a subset of e of t plus eg minus e intersected with det. Lastly, we note that by definition the intersection of the edges in t minus e and det is empty, and therefore to have f in this entire set it must lie in the intersection of eg and de of t, and namely f is a green edge. This is, by our first fact, a contradiction for e blue. And now I challenge you to finish this proof for the case where e is a red edge. This is not entirely symmetric because now we have to work in t hat, but because both trees are really similar, it works out. In total, we get a contradiction out of this assumption, so t slash eg is cycle free, or in other words, a forest. Here, although it is not necessary for the proof, I want to note that t slash eg must also be connected because t is connected, so indeed t slash eg is a tree. So indeed k, which is the number of vertices of that graph, is also equal to the number of its edges plus 1, which equals the number of red and blue edges in t plus 1. We bound this from below by b plus 1 because we assumed that this is not equal to b in the beginning, and furthermore this is equal to r, and therefore we obtain as desired that k is greater than or equal to r plus b plus 2, and therefore we are done.